Hi, everyone. Welcome to the online causal inference seminar. So today we have a talk by Wayne Lam from CMU on greedy relaxations of the sparsest permutation algorithm. In Q&A, we'll have Joseph Ramsey, also from CMU, and Brian Andrews, formerly from CMU, now at the University of Minnesota. Our discussant today will be Alex Markham from the KTH Royal Institute of Technology in Stockholm, and we look forward to that discussion as well. So today, the questions will be handled by Ing, so I'll switch to her to explain how that works.
Thank you, Emma. I will be the Q&A moderator today. Just as usual, please submit your questions through the Q&A section for us to better track it. And we encourage you to submit your question as long as you have it. That's it. Wayne, the stage is yours.
Okay, thank you, Ying, and thank you, everybody. So let me start with sharing my slides. That's it. Good. Give me 1 second.
Great. Thanks, Wayne.
Awesome. Okay, so hello, everybody. So today we are going to talk about greedy relaxations of the Sparsest permutation algorithm, or GRAPS for short. It's a joint work with Brian Andrews and Joseph Ramsey, who are here today, and they will be happy to answer your question in the Q&A. So first of all, I really have to express my gratitude and honor to be invited to give a talk at OCIS, and I hope today you can get some ideas about like causal discovery algorithms, and we hopefully can present that this as a state-of-the-art algorithm that you will use it in the future. And so the slides are already on the OCIS website, and so you can easily get them. And you can also see our contact information here. And so in case you have any questions after the talk, okay, feel free to drop us an email, and we are really looking forward to like more discussion even after the talk. So without further ado, let's start with some background. So the area that we're working is about causal discovery. So causal discovery algorithms has the aim to recover the causal information from the observational data that are generated by a causal mechanism. But this particular procedure of recovering the causal mechanism has to be making some, it requires some kind of assumptions about the true causal mechanism and also the joint probability distributions of the observational data. And there are so many assumptions out there, and one of them, probably the most famous one, is the faithfulness assumption, or the causal faithfulness condition. And so one thing that many algorithms, causal discovery algorithms that are usually labeled as state-of-the-art algorithms, they assume faithfulness. And one failure to causal discovery algorithm, developed by Wang and Uhler, is the Sparsest permutation algorithm, which is a pretty recent algorithm, and we just call it SP for short. It is asymptotically correct under an assumption which is strictly weaker than faithfulness. And I will define what I mean by correctness later with more careful definitions. But the SP algorithm, as you can quote from the name, explores all the possible permutations over the variables. So one problem of SP is that it is super exponential. In terms of numbers of variables, if you have many variables, then the algorithm is not scalable in practice. And so it motivates the search of a greedy version of SP. So to make it scalable. So Solus had last year, they proposed 2 different versions of greedy SP. One is called TSP, which means triangle SP, and the other one is HSP, or ESP for short. They both use depth first search, which is a popular algorithmic procedure over different search space. We'll dive into the discussion of TSP and ESP in the section here. But before we go into detail, we have to introduce some notations to facilitate the discussion of the 2 algorithms. But what do we do in our graphs algorithm or our graphs project? So what we do in our work is that we introduce a permutation-based operator called tab that facilitates the causal search over different DAGs, or what we mean by directed acyclic graphs. There is just a common machinery for causal discovery. So graphs comes in 3 tiers. So there's not just one algorithm, it's a set of 3 algorithms coming in tiers. The basic tier is graph 0, is equivalent to TSP. The first one, okay, sorry. The graph 1 is equivalent to ESP, but it's much more efficient. And graph 2 is our innovation. It's our novel approach that performs extremely well. And I'm going to convince you that soon. But why? What's the point of having 3 tiers? So a higher tier of graphs tries to apply tab, that is the characteristic operator that we have, to a larger set of directed edges. And its purpose is to obtain a strictly sparser estimation or estimated depth. And the good thing about a higher tier of graphs is that it assumes something strictly weaker, okay, layer by layer, for asymptotic correctness. So we will talk more about graphs in this section here. But now, let me try to convince you that it is a good algorithm. And hopefully I can draw your attention here. So graphs 2 gives high accuracy in estimation, even with a relatively small sample size. So as you can see, the performance of graph 2, represented by this little square curve here, okay, they perform extremely well. It outperforms all others candidates that we have tagged. And most importantly, so you can see that in many cases, it approaches almost perfect results. So that's why we are self-confident TL, okay, give a talk about this graphs algorithm and want you to know more about it and even try to work on it or use it in practice. So we're going to talk more about this performance statistics in the simulation section. But now, let's first dive into some notations that we need to talk about each of this, GSP, ESP, and graphs. So, like the standard discussion in causal discovery, okay, with the assumption that which is causal sufficiency, we don't have latent variables, we use a DAG. But G here over a set of measured variables. I believe that our audience generally are familiar with DAGs, directed acyclic graphs, and the related graphical locations, including parents, children, and these separations. So I won't go over the details, or I won't go over the graphical definitions. But that said, let's see how a DAG looks like. So it comes with vertices. So each vertex is an integer. So let's say we have m of them. And the vertices could be connected by directed edges. Okay, so there is only one directional, there is no there is no bidirected edges. So each particular directed edge represents a causal inference or direct causal inference from one variable to another variable. And we also have the standard notation deseparation defined, okay, in many places, including the prose work. And so this separation relation is a graphical concept that represents the flow of causal information in the DAG. For example, if we have vertex 1 pointing to vertex 2, pointing to vertex 3, then we say that this particular relation from 1 to 2 to 3 has a particular causal information flowing from 1 to 3. But it can be blocked by 2, that this 2 is the vertex blocking the causal information flowing from 1 to 3. So we use the standard, on the other hand, we also want to talk about a jumpable distribution of the observational data. So we use P over the same set of variables, and we use the standard notation, conditional independence, to notate the conditional independence relation of, for example, the set of variable X, the set of variables Y, given the conditioning set Z. Next, we want to talk about what a causal model is. A causal model is just a pair of a DAG on the one hand, and a joint probability distribution on the other hand, over the same static variables. We use G star to represent the true data generating causal mechanism, the true DAG. And so now G star P, this pair becomes a true causal model. And also, for instance, classical representation, we use I of G, which is the independence model of G, to represent the set of deseparation relations that held in G. And we can say that these are the deseparation relations entailing the conditional independence encoded by the DAG. So I of G looks like this. It is a triple of, okay, the independence or deseparated north and or deseparated set of vertices conditional on a particular set of vertices. Similarly, we have that for the probability distribution over the independence relation. So we will be comparing IG and IP a lot. As said, when we want to do causal discovery, we need to make some assumptions over the true causal mechanism, how the true DAG and the true probability distribution relate. And these are the assumptions that are widely used. First, let's denote some notations here. Let this whole forms DAG V represent all the possible DAGs over V. So you can imagine that each DAG represents a causal hypothesis over the joint probability distribution. So now, right here is a set of all possible hypotheses over the distribution. So now, the first condition that we want to study is the causal Markov condition. Sometimes we denote it as CMC. So we say that a DAG is a Markov to P, the joint distribution P, which means that the independence encoded by the graph is a subset of the independence that held in the distribution. So this particular assumption is widely made, but this assumption by itself is insufficient. You can hardly recover much causal information of the true causal mechanism because, for example, every complete DAG. What is a complete DAG? A DAG is like every pair of vertices they are connected with a directed edge. It's also Markov because they entail no independence relation. So this one is empty. So that's why we want to introduce extra assumption. One of them, the very widely discussed the assumption is called the causal favorless condition, or sometimes just favorless for short, or CFC for short. So it requires not only Markov, it also requires that all the independence that we see in the joint probability distribution, they are encoded by the graph. So which means that the graph and the distributions, they encode the same set of independence relations. So it seems like favorless is a good assumption to be made because in that case, we can recover a lot of causal information. But that said, okay, favorless is not doing all the things that we want. We cannot just recover all the things, for example, true causal mechanism. What we can do is to recover the true Markov equivalence class at best if we only rely on conditional independence relation. So what is a Markov equivalence class of a DAG? It means that they are the class of DAGs that share exactly the same set of entailed deseparation relations or conditional independence relation entailed by the graph. We say that a causal discovery algorithm is correct if the output is the Markov equivalence class of the true DAG. So some classical algorithms, some classical causal discovery algorithms, including GS and PC, they assume that the true causal mechanism is Markov and favorable. But the problem is, okay, almost violation of favorance. What does it mean? Near violation of favorance or almost violation of favorance means that we may mistakenly take, for example, dependence of independence or the other way around, so in hypothesis testing over the observational data. And so when you are given final sample, then it is possible that you get a misjudgment about independence and dependence. So in that case, even their favorableness in the population may be true, okay, theoretically. But in practice, we see some problems that the assumption doesn't help. So that's what it motivates the design of causal discovery algorithms that are correct under assumptions that are strictly weaker than favorless. So I will present it by a spectrum. So on the one hand of spectrum, we have favorless, on the other hand, we have micro. So we want to focus on something that lies between favorless and micro, but still correct in the sense that we can recover the true micro equivalence class. So we denote. Okay, so maybe before I explain the terminologies here, so one approach that developed by Wang and Uhler is the unique frugality assumption. Sometimes it's also known as the Sparsest Markov representation in their literature, okay, in their writing. So I denote this FR as a set of frugal decks. What do we mean by frugal? Which means that a deck is frugal if there is no Markov deck which is strictly sparser, having strictly fewer number of edges. And uniquely frugal, which is just adding a U to frugal, which means that all the frugal decks, they have to belong to the same micro equivalence class. So when we say that unique frugality assumption is satisfied, which means that the true causal mechanism or the true deck belongs to the, again, not only the sparse graph, but also that it is unique in the sense that all other sparse graphs, all other sparse stacks, they belong to the same MDC. What the SP algorithm does is that for each particular permutation, we come up with a deck, we construct a deck, we call it GPI with respect to the distribution. For each permutation, we do the same thing, and now we return the sparse. Okay, I think I found a typo here. Okay, we return the sparse set of decks. So how does it work? If you are given a graphoid, what is a graphoid? A graphoid is a particular set of properties about the joint distributions. So I'm not going to go over them, but there's a hyperlink here, so interested audience can go into the link and see the details of what a graphoid is. So what they show is that the SP algorithm is correct under unique frugality. And so now we see that they successfully found a point between favorless and Markov, which is strictly weaker than favorless, that we can recover the true micro equivalence class. But one problem of SP is that it needs to exhaust all the permutations over the variables. So for example, if you have 10 variables, then you have 10 factorial permutations, which is more than 3 million permutations out there. So that's why in practice, SP is not scalable. That's why it motivates the search of the correct but greedy versions of SP. Greedy in the sense that it, okay, doesn't have to go over all the possible permutations. So what exactly, okay, what's the point of doing permutation algorithm? Okay, we are going to explain all the details or intuition of using permutation-based algorithm. But first of all, what do we mean by permutation? Is just possible orderings over the vertices. For example, if we have 1, 2, 3, 4, 2, 3, 4, 1 will be a possible permutation over the set of vertices. 3 here means the set of vertices preceding a particular vertex I in the permutation. For example, 2, 3, 4, 1 is a permutation. What goes before 4 is 2 and 4. We say that a permutation is a causal order of a particular deck if every vertex, for every vertex and every ancestor of that vertex, they always go before the vertex in question. For example, if I have a particular vertex I and all the vertices, let's say they go to J, okay, each of them is J, then we'll say that J has to go before I if J is an ancestor in the graph. So now what we do is that we can construct a deck from a permutation using this particular condition called RU, which is my square word. But or maybe that's kind of hard to read, but what I want to mean here is just that J, okay, when do we draw an edge between J and K, from J to K. There's a J, first of all, persists K imply, and they are dependent, just here, given all other vertices that goes before K. So now, for each permutation, we have a DAG. So here is an example. Let's say now we have only the marginal independence between X1 and X3. So now we do not have, okay, we still have the 1-3 edge because they are marginally dependent, but not conditionally independent given 2. So that's why we have the 1-3 edge. All other edges are here because we don't have their independence. But on the other hand, if we change the permutation from 1-2-3 to 1-3-2, we now have the independence represented by the non-adjacency between the two vertices, according to the RU condition. So one motivation of using permutation-based algorithm is that each particular induced DAG, that is a DAG constructed by a permutation, is necessarily SGS minimal, as proven in Fermat and Pro. What do we mean by SGS minimal? First of all, this term is coined by, Gigi Zhang, but this term can originally come from the minimalistic condition discussed by Sparsest et al. In causation prediction research. What we mean by SGS minimality is that if that is SGS minimal, there's no proper graph of G, which is Markham. We go back to the last slide, which means that, for example, for the graph on the left, you cannot take away any of the edge here, but still having the Markov relation. So now we can talk about TSP. So TSP relies a lot of the chickening results, which is a famous result in total discovery. And so we're going to dive deeper about the chickening algorithm and the chickening sequence. But first, what we mean by a covered edge, for example, J to K, which is a directed edge, is covered in a particular DAG, which means that they share the same set of pairs, except for K, which has a parent of J. So the chickening algorithm represented by a theorem here says that, so if the independence entailed by H is a subset of those entailed by G, then there is a sequence that we label them as a chickening sequence from H to G, such that it's like G1 to GK, where for each particular independence, we still have the map from the I to the I plus 1. The mapping is preserved. And the subsequent DAG, Gi plus 1, is obtained either by reversing a covered edge or deleting a directed edge in the prior DAG. What TSP does is to perform a depth search over the chickening sequence, starting with a joint probability distribution, which is a graphoid, and a particular induction permutation. What they do is first is to induce a DAG, perform depth search to identify a SGS minimal DAG. They keep doing it until you cannot find an even sparse DAG. For example, right here, we start with the induction permutation 132. We construct the DAG, then reverse a couple edge to form G2, and then you find that, okay, this edge, the one edge can be deleted. And so now you form an SGS minimal DAG. You keep doing until you cannot find a sparse DAG. What TSP does, or what TSP is guaranteed, is that its DAG returned it must be pro-minimal. So what do we mean by pro-minimal here? It means that, okay, no Markov DAG that can entail a proper superset of independence relation. So I have a formula defined here. So which means that there is no way that you can entail more independence. So now we can see that the nice feature of the TSP is that it will guarantee that the return the DAG is pro-minimal, but I also want to introduce another condition, which is called unique pro-minimal, which is not really popular in the literature, but will be proven useful later. It's just required that all pro-minimal DAGs they are in the same macroequivalence class, just like the relation between frugality and unit frugality. Now we're going to see why. Okay, we're going to see soon why there's an important assumption relevant to TSP. Solus et al. Also discussed a TSP condition, that is when TSP is correct. So when we say that TSP condition is satisfied, which means that the DAG returned by TSP is in the macroequivalence class of the true DAG under every initial permutation. What proven by Zhang is that when faithfulness is satisfied, then the set of faithful DAGs is just the same of pro-minimal DAGs, it's just the set of macroequivalence class of the true DAG. Therefore, TSP, which guarantees that the output is pro-minimal, is correct under faithfulness. They claim that TSP condition is slightly weaker than faithfulness. However, their claim is false. So indeed, faithfulness is necessary for the correctness of TSP. So what I've shown in our paper is that faithfulness and unique pro-minimal are the same. And it is a very important logical discovery in the literature, which gives you an other interpretation of what faithfulness means. And we also show that TSP condition is just faithfulness. Okay. I'm not going to go over the details here, but now we have a question. If the point of introducing a greedy version of SP is to weaken faithfulness, now we are going back. We didn't have a algorithm which is correct under faithfulness. Okay, under conditions slightly weaker than faithfulness. So how about a weaker version of SP, which is namely ESP? So the idea of ESP can be represented geometrically. So first of all, we can form a permutation which looks like this over the permutations. So now we have 3 vertices. So there are like 6 possible permutations over the set of variables, and they are connected by the so-called adjacent transposition. So in order to explain that, it's better to go into the diagram here. Is that of a formal definition. For example, 1, 2, 3 is connected with 1, 3, 2. Why? Because you can easily swap 2 and 3. They're adjacent in the permutation in order to obtain at 1, 3, 2. Similarly, you can swap 1, 2, 3 to form 2, 1, 3. So on and so forth. So it forms a very natural search space for permutation search. But an even more natural way to perform search is to contract the permutohedron to a DAG associated hedron. A DAG associated hedron is obtained by collapsing the permutations that induce the same DAG. For example, 1, 3, 2 and 3, 1, 2, they can induce the same DAG if, in the last example that we discussed earlier, where 1 and 3 are marginally independent, and so they will both induce the unshielded collider here. Whereas the all other 4, they induce different DAGs. So now we collapse the left to the right and use this as a search space for ESP. So ESP performs a greedy DFX over that associated hedron, as shown in the last slide. So they just perform walk. They walk around the associated hedron, and to make sure that, okay, every time you walk around, it's weakly decreasing. That is, you decrease the numbers of edges. So right here, this is a weakly decreasing walk because you, okay, have 3 edges to 2 edges. But in case if you see something like 2 to 3, like this, that is not weakly decreasing. So they keep doing it until no sparsest that can be found. So what proven by Solus et al. Is that the ESP condition defined very similarly like the TSP condition is slightly weaker than the TSP condition. So which is something like here. But one problem, okay, so first of all, the happy result is that now we find an algorithm that is correct even under unfaithfulness, which is weaker than faithfulness. But there is an unhappy result. The unhappy result is that they didn't really implement ESP. Why? Because it's not scalable. Why is it not scalable? Because they need to compel the DAG associated hedron in advance before really performing the data search. But you can imagine if you have a lot of variables, it is really hard to compare to that associated hedron before you perform the search. So that's why, literally speaking, we don't have a nice algorithm which is scalable and we could have favorites. So is there any efficient way to implement ESP such that it's scalable and there's one task that we want to handle by graphs? What graphs does is that it uses a single, just one operation called tug, which is permutation-based over the 3 algorithms. Graph 0, we prove that it's equivalent to TSP. Graph 1 equivalent to ESP, but much more efficient. Why? Because we don't have to compare the data associated hedron before performing the data search. We just find labor immediately. Graph 2 is our innovation, which is superscale, as I showed before. A higher tier of graphs requires a strictly weaker assumption. So just like what we represent here. So that's why first it performs better search in terms of performance, and it also requires a strictly weaker assumption. So that is exactly what we want to do in order to find something wicked and favors, but at least assuming uniformity. So why do we have 3 tiers of graphs? 0, 1, 2. What do they mean? Actually, they just mean the different ways to apply the tug operator that we are going to explain in the next slide. So 0, 1, 2 represent 3 different types of edges. 0 means coupling edge that we have discussed before. 1 means singular edge, which is neutral. A singular edge is an edge that you only have one way. For example, a singular edge between J and K is that you only have one way to go from J to K. You don't have another pathway going from J to K. There's only one way to go from J to K. So that's what we mean by singular. There's singular pathway. And when T is 2, it just means all the edges or the general set of edges. And using singular edges, we can characterize the neighborhood of a deck associated hedron. But how to walk in a deck associated hedron, we need an operation, which is called tug. I really like the tug idea, and we're going to explain it in a more metaphorical way. But the general idea is this. Let's say we have any pair of vertices J and K, where J goes before K in pi. And so we can easily rewrite pi in terms of something like delta 1, J, delta 2, K, delta 4, which is put them into segments. But now we want to do some minimal change with respect to pi, not trying to change delta 1, not trying to change delta 3, but just trying to change what is going on J, delta 2, and K. We partition delta 2 into 2 sets. The first set is called gamma. Gamma is just the ancestor of K. And the gamma complement is just the set of the non-ancestor of K. We arrange them such that ancestor go first, and then K, and then J, and finally the non-ancestor of K. And so now, what's the intuition here? And why is the name tug? For me, what I understand tug is just like tucking a shirt. It's like tucking a shirt into your pants, okay? So now we want to talk about how to tuck a shirt and also like when to tuck. So we want to talk about when with respect to like which particular kind of edges that we are tucking. And then let's imagine this like tucking a shirt. J is like your pants. K is like your shirt. You're trying to change the order of the shirt and the pants just to tuck it in, right? And now what's delta? Delta 2 here is like, for example, the gamma here of delta 2 is like your undershirt. You want to tuck your undershirt first and then your shirt, and so your pants. And right here, you can see the left arrow here will be like your body. Okay, so you're moving the things closer to your body. But how about this? Okay, gamma complement. You can imagine this is your belt. You don't want to tuck your shirt between your belt and your pants. So that's why the belt will be pushed like here. But you can say the delta 1 will be maybe your underwear, or delta 3 will be your jacket. Okay, so there's one way metaphorically to understand how tuck works. We have an example, okay, showing you how tuck actually works, okay, in a mathematical setting. But sadly, I don't think I have enough time to cover them. But given that you have the slides, so you can go over the example to see how we really apply the shirt, the belt, the pants idea here. So right here is the pseudo depth research. Basically, we just apply it by first. Let's have a look at the algorithm first. Okay, we have distribution, we have initial permutation, we have T, which represent the tiers of graphs or the type of directed edges. Depth research comes with the depth, okay, which is the upper band, and R is just dummy operator recording recursive core. So we keep tucking, okay, for each edge in the deck. We perform tuck, so we come up with a new permutation, we construct the deck and see if the score is better. Okay, if the score is just the same, then we keep doing the same thing. We keep using this recursive function. But if it's a better score, then we turn the deck. We turn the sparser. We turn the better permutation. And graphs is just using this particular recursive function, this step search. But it first start with graph 0. Right here is a recursive port. We start with graph 0. If, okay, you want to start with graph 1, that is okay, but you start with graph 0 first before you do graph 0. Similarly, if you want to do graph 2, 0 first, okay, 0, 1, and then 2. You keep doing until you cannot find a score improvement. But what do we mean by score improvement? So right here, score means negative edge count. That is sparser, okay, fewer number of edges. In practice, you can also use PRC score with respect to the observational data. T, just what we explained, it's just a T of graphs, the type of directed edges. And D refers to the depth of the depth of search. It's a band. And if we set D to infinity or just like the factorial of the number of vertices, then we call that unbounded. You keep one, okay? In practice, we don't do it, okay? But in theory, we just say unbounded. In practice, we can choose some very small d, like 3. Also, we assume that depths cannot be revisited. Otherwise, we can keep going between the two depths in an infinite loop. What we prove is that when we use unbounded graph 0, it always returns the same deck as TSP. It's not asymptotic, it's just trick, okay? It just perform the same operation as TSP. And graphs 1, unbounded, is just like ESP. They always return the same deck. But now, the important thing is, graphs 1 is scalable. ESP is not, because ESP has to compile the entire deck associated header in advance before the depth search. But graph 1 doesn't need that. Graph 1 can learn the labels by just tucking singular edges. So that's why it is efficient. But how about graphs 2? Graphs 2 goes beyond graphs 1 by tucking not just singular edges, but tucking all possible edges that you can see in the deck. So that's why it has a wider search space, and it allows a possibility to search for even sparser depth. So that's why we'll say that graphs 2 is more powerful than graphs 1 in terms of the reason to find a sparsest permutation or the sparsest depth. So, as we have argued before, if you want to do causal discovery, you need to make assumptions over the causal mechanism that is between the true deck and the distribution. There are so many assumptions discussed in the literature. Of course, we see Fabler's, we see Markov, and we also discuss like the spell. And we also prove that these are the same, okay, because TSP and graph 0 are the same, so these conditions are the same, okay. This is also proven. And right here, now, we can talk about graph 2. Where is graph 2? Graph 2, of course, is strictly weaker than graph 1, but still is strictly stronger than uniformity. What does it mean? It means that graph 2 is not correct only under uniformity itself. It assumes something stronger than uniformity. We can find counterexamples or counter models that graph 2 cannot return the sparsest permutation, like right here in this interval. But still, scalable, and it is assuming we could have vapors, so that's why it does better than TSP and ESP. So we have the asymptotic result here. Now we can talk about simulations. So this part is about how we construct a DAG. Before we say we construct a DAG by independence relation, okay, so going from the pi to G pi, we have to look for dependence relation in order to determine whether we add the edge or not. But in practice, maybe you don't want to do independence steps. So we can use, for example, BIC. Right here is another way to construct DAG using the identification of a Markov boundary given a DAG. Okay, a Markov boundary of a vertex or of a variable given a relative set of factors. We use the goal string algorithm to identify the Markov boundary, so which is shown to be asymptotically correct. If you have a graph here. And the general setup of our simulations is that, first of all, we have tested multiple settings, not only linear Gaussian, but for the sake of simplicity, I think maybe we can just talk about linear Gaussian today. We also tested on real data as well, and it also performs well. And I believe that our audience are familiar with linear Gaussian models, so I'm not going to dive too much into it. It's just, okay, each variable is a linear combinations of the parents and the noise term, okay? And the coefficient, we pick it from a uniform distribution between -1 to 1, not including 0. And the noise terms, they are standard Gaussian, and they are pairwise independent. We have a penalty term, the penalty term for BIC is 2, and the significance level that will be used for independence test for PC is something set to 0.001. For graphs, we set up a particular depth. Not too high, just gray. If it is covered or uncovered, then we will just pick 2. So we won 20 times over each particular simulation setting. Okay, then we compare the true CP DAG with the estimated CP DAG. What I mean by CP DAG is just a graphical representation of macroequivalence class. That is, now we are comparing the estimated macroequivalence class with the true macroequivalence class. And here is how we shall, like, if you fix the number of variables to 60, even you only have 1,000 sample size, if by varying the average degree, there's a number of labors for each particular, the average number of labors for each particular vertex, you can see that generally, most of the algorithms, they decline, okay, they perform, okay, worse when you have a higher degree. But it doesn't matter much for graph T, represented by this little square box here. When you increase the number of variables, but keeping, okay, the sample size and average degree, you can still see that we are doing very good, okay, even with a lot of variables, okay. But now, one thing you can see is, like, usually PC, okay, one state of the algorithm is known best for its adjacency precision. We are competent like PC, but we perform much better than PC in other domains. So one shortcoming of graph 0, of course, because it's tier. You want graph 0 first, and graph 1, and graph 2. So you can see why graph 0, which is represented by a triangle, goes below, and then 1, and then 2. Okay, so it is just represented by the tiered ones. Even though it sounds like, oh, graph 0 takes a lot of time, is it? No, even for 100 variables. Right here is still less than 2 minutes. So, which means that graph 0 is a scalable algorithm, even for 100 variables. So, now let me conclude by some possible, okay, future work that we can develop from this graph project. One thing is more theoretical, is about what we use as a scoring criteria. We can use BIC, we can use negative edge-can, but sometimes we can think about, like, the spartest model may not have the fewest parameters. In the linear Gaussian case, they are the same, but in the non-linear, or maybe in other cases, or for example, in the multinomial case, they're different. And so should we assume something different than uniformity? Maybe unique parameter minimality? That's a theoretical discussion that I'm trying to work on it. Another thing that we can do about graphs to improve that is to make it less greedy. What I mean by less greedy is that when we record the procedure of doing like depth research, we make the score weekly improve. But what if we allow some kind of like score to decline? Okay, we go back and then we go up. Okay, we go back and we're good. So we have some decline and then we improve again. Is that okay? If yes, then we can easily find even sparser graphs. How about implementing graphs with some latent variables, like mixing it with FCI, so we can develop this graphs from a causal sufficient setting to a causal insufficient setting. And lastly, of course, it's like what most people would do. It's like compare graphs to a more comprehensive context, and also on different possible settings over, for example, different distributions and real data. So these are the references probably people will be interested after the talk. But one last thing that I really want to say is like, if you have the cell phone, take it out, you can scan the QR code here, so you can get all our paper, you can get our content, you can get our data, and you can get almost everything about this graph project. And so I have to, again, re-express my honor to be giving a talk in this OCI seminar. So all comments and questions are most welcome. Thank you.
Thank you, Wayne, for the great talk. I think Joe and Brian has asked a few questions. We still have one question left. Maybe we can answer it. So it asks, are there any possibilities to draw a scalable algorithm from the literature on large networks or even topological computation, say, related to simplicial complexes, which are related to networks?
Simplicial complexes. I'm not completely sure. Okay, so I'm very sorry that I cannot like answer it like right now, but there's definitely a question, because like now the question is like how to represent the search space more geometrically, but still making the scale. So what I'm thinking is like, if you go back to like discussion between ESP and graph, so now what's wrong or what is lacking in ESP is that, yeah, we come up with search space, but the question is how to move around the search space. So which means that you still need an operator. So not only search space, you need an operator that tells you how to move around. So what I'm thinking is like, yeah, let's say now we come up with a search space, which is different than a depth associated. But the next question is like, so how to walk around, which is in a scalable way such that we have an operator that defines over the search space to facilitate the work. I'm not completely sure, but I will definitely look into it. I'm doing a cap screen here, so in case I forget the question. Okay. Yeah, but thank you for the question. It's a very nice one.
Thank you for your answer. Yeah, we'll also send you the Q&A for your reference later.
Thank you.
Yeah. I think without further ado, let's head to the discussion. Alex, please feel free to share your screen.
Looks great though. I just cannot hear you yet. Sure. Okay. Seems like we're having some technical difficulties, so just give us a second.
Okay.
Yes, we can hear you now. Perfect. Yes.
Okay, then share my slides again. And oh no.
No worries.
Now.
Yes.
Oh, good.
That looks great.
Okay, great.
Yeah.
Yeah. Okay. So sorry about that. Yes. Hello, everyone. My name is Alex Markham. I'm a postdoc in the Math of Data and AI group at KTH. And yeah, first, thanks to the organizers, and I'm very happy to be here and discussing this paper of greedy relaxations of the sparsest permutation algorithm by Lamb, Andrews, and Ramsey. So here's an outline of what the discussion will be about. So I'll start with just a recap to try to emphasize the kind of most interesting aspects of the paper in the presentation from my perspective. And then once we kind of have that in common, I'll try to explore, like, can we get an understanding of how GRASP performs and how understanding this tells us something about the space of DAGs, the search space. And then from there, I'll suggest some what I think are interesting follow-up questions and work. And yeah, so in their paper, Lamb, Andrews, and Ramsey achieved state-of-the-art performance and reasonable runtime and scalability. So for a machine learning paper, that's already very good. But to me, even more interestingly, they have, I would say, substantial theoretical contributions. And so they're able to achieve this performance and this scalability, even while weakening faithfulness assumptions. And the two most interesting theoretical contributions to me are that they define singular arrows in DAGs. And this definition of a singular arrow helps neatly characterize all edges of the DAG associated hedron. So I'm doing a postdoc with Liam Solus, the author of this paper that was mentioned. They kind of did some of the work on ESP and TSP, and that made the algorithms for learning DAGs using these permutation-hadrons and association-hadrons. And in their work, what's missing is a full characterization of these edges. And so it's very interesting that this definition of singular arrows of DAGs helps give us that characterization. The other interesting theoretical contribution of this paper to me is their tuck operation. And so they generalize this adjacent transposition operation of variables in a causal order. And so in ESP and TSP, you've got this permutahedron, and your operator is kind of very simple. It's just you reverse two adjacent things in the permutation. But here they've generalized that in an interesting way with this tuck operation. So that's the recap, and it highlights the important, or to me, the most interesting theoretical points of the paper. And so now, with that highlighted, I want to try to understand why does GRASP perform so well. And to do that, I'll start by comparing it to the first, I think, or at least a very kind of old and well-known greedy search algorithm for DAGs called GES. So it stands for greedy equivalent search. And I like to think of GES from a combinatorial perspective. And so what I mean by this is that if you imagine the entire space of DAGs, then you partition this space into graphically defined equivalence classes. These are Markov equivalence classes, and they're defined graphically so they can be represented by a mixed graph with some directed and some undirected edges called the CP deck. And this gives you kind of structure, and the moves that GES makes to greedily explore this space are inspired by this combinatorial structure. And so I'm going to speak a bit maybe abstractly to just try to give you the intuition of how GES works. So if you just imagine a kind of tree-like structure, so maybe at the base is the dependence model. So it's a fully connected DAG, and this DAG is Markov to all probability distributions. And now at the top, the very top of the tree, you've got the independence model, a completely empty graph. And so using like a sparsity assumption, so GES starts at this empty graph, and it works its way down the tree towards the base, increasing the score as it goes along. at some point the store stops increasing. So then it starts going back up towards one of the branches until the score again stops increasing. And so GES greedily kind of works in this very, from one perspective, restricted way of starting and going along these branches. In contrast, GRASP offers more flexibility, of course at more computational cost than GES moves allow. But this flexibility gives GRASP the sort of, it allows it to avoid local optima. So while GES is traversing this kind of tree-like structure, it's prone apparently to getting stuck in local optima. But GRASP is sort of able to jump between branches, whereas GES has to be able to traverse the whole kind of point of the tree. And so, yeah, I'm suggesting that GRASP performs better because of this. And this is sort of, this observation is maybe in line with an observation that can be made from this 2012 paper by Hauser and Buhlmann and their algorithm GIES. So it's greedy interventional equivalent search. That algorithm differs from GES in that instead of just these two phases of going kind of down the tree and then back up, it cycles through phases. So it moves down and then does what's called like a turn phase and then moves back up. And it repeats this cycle. And similarly, that allows it to avoid local optima. So GIES performs better than GES by avoiding local optima. And yeah, I'm suggesting GRASP is similarly able to perform better than GES in this efficient greedy manner by avoiding the local optima that GES is prone to because of the flexibility of moves that GRASP is able to do. Okay, so with that kind of comparison to GES, now I want to specifically compare GRASP2, which is the especially novel algorithm that Wayne just presented, with GRASP1 and GRASP0, which are equivalent to ESP and TSP, which is previous work by Teyssier and Solus and Wang and Uhler and people. So greedy SP, I would describe it as coming from a geometric perspective. So it starts by, we think about a set of points. Each point represents a different permutation. And similarly, a different permutation, and corresponding to that, there's a different minimal I map or independence map of the, And then with all these points, we form a convex hull. We take the convex hull and we get a polytope. And the moves that greedy SP makes is they correspond exactly to walking along the edges of this polytope. In contrast, GRASP2, also with increased computational cost, if you imagine this polytope, GRASP2 doesn't just walk along the edges, it's able to jump between points that aren't necessarily connected by edges. And I'm suggesting that this ability to jump between these points that aren't connected by edges allow GRASP2 to better handle near violations of faithfulness. Okay, and so the point of the slide is to give kind of a few different perspectives and some sort of context or broader background of greedy causal discovery algorithms. We can think of GES from this very combinatorial perspective. We can think of greedy SP from this very geometric perspective. But the interesting thing about greedy SP, about GRASP and about GRASP2 is that it's not so obvious what it does from a geometric perspective, because at least as far as I'm aware, there's not a clear sort of understanding of which points it jumps between in this polytope. And similarly, in the paper, it is framed sort of in this hierarchy building from GRASP0 and GRASP1. And so it also doesn't have a, so far, clearly presented kind of combinatorial perspective. And so, that leads to some natural, interesting follow-up questions, such as, can we give GRASP2 a geometric interpretation like ESP and TSP? So can we relate this polytope, this diagosocihedron, to some other polytope such that the edges or facets or something of that polytope correspond to the moves that GRASP2 is making? I think another interesting question would be to just a very different direction, just sort of abandon the geometric holdover. So GRASP0 and 1 were motivated by this geometric understanding of this polytope, but GRASP2 in its permutation-based operation, this tuck operation, it sort of abandons that, or at least doesn't have a clear connection to this geometric space. And so maybe we can have a better understanding of what GRASP2 is doing by trying to look at it from a different perspective. So for example, it's a permutation-based operation. Can we look at these permutations more algebraically? Is it some group action? And or can we look at it more combinatorially? Can we talk about equivalence classes of graphs that GRASP2 is moving between? So yeah, I think that would be an interesting question that's sort of a different direction from giving GRASP2 a geometric interpretation. And another question would be, can we define other useful permutation-based operations? And finally, can we use some of these ideas developed by GRASP2 to explore graphs other than DAGs, such as CP DAGs or ancestral graphs? Yes, so thanks, and I'm very interested to hear the author's response.
Thanks, Alex. Very nice comparison. Great. So we are kind of short on time, but Wayne, if you would like to respond briefly to some of Alex's points or comments.
Okay. Yeah. So because there are a lot of points that Alex mentioned that I really like, and so, but maybe let me focus on one particular problem that Alex mentioned. So GRASP2, unlike GRASP0 and unlike GRASP1, which is like TSP and ESP, it doesn't come with a nice geometrical representation. That is true. Okay, it is obviously true because like we can have a particular DAG in a DAG associated hedron. If we tuck away from that particular DAG, it can come with two particular permutations for that DAG. They just tuck away differently. So even though we have a one edge in that DAG, we can come up with two different DAGs because of the two possible permutations that are consistent with the original DAG. So which means that in that case, we don't have a nice way to represent it. So that is a difficulty of understanding how GRASP2, unlike GRASP0 and GRASP1, that can be pictorially represented by a nice geometrical search space like a polygon. But on the other hand, so the other question that others ask is like, so is it possible to move away from DAGs? Let's say move to CP DAGs. Yeah, I think it is possible. And Brian and I have been thinking about this question for some time, but it is still unclear, especially if you understand it from a permutation point of view. Because like for different permutations, for different graphs in the same macroequivalence class, 1 to 2 to 3, 3 to 2 to 1, they have very different permutations, right? And so how do we have a particular operator that moves along a space of, let's say, CP DAG associated hedron? We don't even know whether it forms a polygon or not. And we don't even know whether we can have a particular efficient operator to move along this possible search space. But they are very interesting questions that we would like to develop. So thank you, Alex.
Great. All right. So we'll wrap this up. Thank you both for your talks and discussions. All right. All right. Good. Okay. Yes. So you probably don't see me now. Just 1 second. There we go. All right. So thank you, Wayne, and thank you, Alex, for nice talks. Very extensive overview over these topics and a really nice interpretation of the tuck process. I think we'll all remember that. I at least will. Very nice illustration. Okay, so next week we'll have a talk by Jose Zubizaeta from Harvard University on bridging matching, regression, and weighting as mathematical programs for causal inference. So hope you all join us for that. Thank you all.